As I said, my name is Olivia Wanless. I am a senior electrical engineering student at Kettering University, and my research project focuses on the role of social responsibility and safety in autonomous vehicle development. As an introduction, this research was conducted as a part of the AutoDrive Challenge, which is a 4-year program in which university teams in the US and Canada compete to build an SAE Level 4 autonomous vehicle. Pictured on the screen here is all the teams and sponsors together at last year's competition in Ann Arbor, Michigan. As a part of this competition, teams are required to write a report that addresses social responsibility in some way. I led the effort each year for that for my team, and last year the focus of the report was how can my team make a case for how an autonomous car could safely navigate the streets built for non-autonomous cars and composed of mostly non-autonomous cars. The objective of this research was further defined by the rules and our team's interpretation of them. We needed to recommend how to make autonomous vehicles safe by defining behavior on a specific model by Mobileye, which is called the Responsibility Sensitive Safety, or RSS model. An image from that model is shown on the left, which I'll explain some more in the following slides. We also needed to address how to safely test pedestrian detection systems and how to communicate with and educate consumers about the new technology that's going to be coming out. Our approach was to start by selecting our topics based on the rules. We then conducted our research by combining our findings from the various online reports, data sets, and studies, screenshots from some of which are shown on the left. Based on those findings, we identified the gaps that existed in literature, data sets, and policies in order to recommend changes, which we worked to implement on our own vehicle and practices. The RSS model that I mentioned earlier is just a framework for defining ideal vehicle behavior. Another image from that model is shown here on this slide, and this image tries to define safe following distance by outlining the distance required between the vehicles if the front vehicle applied maximum braking acceleration and the rear vehicle applied maximum acceleration forward until noticing braking and then applied minimal braking until coming to a stop without hitting the front vehicle. And if that maybe seems somewhat confusing and vague, then you'll understand the issue that we found with this model, which was that it really doesn't adequately define the parameters that it uses. There was no real definition or way to determine the accelerations in that figure, and therefore the model can't really be applied without additional definitions. The next area that we investigated is diversity in pedestrian data sets. These data sets are used to train neural networks or to test computer vision algorithms, both of which can be used to detect pedestrians. Obviously, there are a lot of facets to physical diversity, which can include height, weight, race or ethnicity, male or female, age, and even clothing choices. Many of these characteristics are shown in these screenshots, which were taken from the JAAD dataset. One characteristic that we really weren't able to find in our research was mobility aid users. Other than strollers, there were very few to no images of mobility aid use in any of the dataset images that we looked at. This is a real problem, especially considering that wheelchair users were found to have a 36% higher fatality rate than non-wheelchair users when they were involved in crashes with human drivers. This presents a really clear opportunity here for autonomous vehicles to improve on our current conditions, but obviously that can't happen without mobility aid diversity and images used for training. Next, we moved into how consumer perception is impacted by what people read and see in the news. There have been several highly publicized crashes involving autonomous vehicles in the past few years. You may remember the Uber crash that killed a bicyclist in early 2018, or several Tesla crashes that were essentially related to a lack of knowledge about autonomy and the capabilities of the vehicle. Even though some of these crashes, particularly the Tesla crashes that I mentioned, didn't really have anything to do with the failure of the autonomous technology itself, but rather with a lack of user knowledge on what the car could do, they still had a really significant impact on consumer opinion. Following several crashes between December 2017 and April 2018, the percent of consumers who were willing to ride in an autonomous vehicle dropped from 37 to 25%. There were also several incidents that involved consumers attacking Waymo autonomous taxis, which are shown on the left here, even though Waymo wasn't actually involved in any of those publicized crashes. Clearly, something needed to be done there to help reduce those crashes. And while safe testing policies for companies are necessary, we also wanted to find out what could be done to help consumers truly understand the capabilities of their vehicles. And to that end, we quickly found a study that was conducted on the aviation industry several years ago. This study found that increases in airplane automation actually increased crashes for a period of time after implementation. You can see those rises and falls on the graph here after new technology was introduced. And to help deal with that, after several other failed attempts to figure that out, the industry began trainings that were based on identifying exactly what pilots didn't understand about the capabilities of their new systems, which proved to be very effective in flattening this graph down the road. Another area that we found to be helpful in increasing understanding is just something very simple, color. If you take a look at the three shapes at the bottom of this slide, they probably stick in your mind a lot better like this than they would like this. That showed us two key things. First, that training was necessary to curb airline crashes that were caused by a lack of understanding of automation. And second, that color can somehow be used in that training to increase learning and memory performance. And I'm going to address our conclusions based on what we actually worked to implement in our own team practices. First, to deal with the poor definitions in the RSS model, we used trained drivers to conduct testing that defines our vehicle behavior by defining the items in the RSS framework. And the reason that I specify that they're trained drivers is that we need to make sure to avoid biasing the vehicle's behavior from unsafe or poor drivers. To help combat the gaps in pedestrian data sets, we also have taken several of our own images to help fill those gaps in our detection systems. In order to address both the lack of understanding that causes crashes and to inform consumers about what really happens in autonomous vehicles, we propose two systems. First, we propose a standardized set of colors and patterns that would be used on every steering wheel in order to signify the level of autonomy of the vehicle. The color system would be used because of the benefits of color and memory retention, and it's used in combination with a pattern to prevent issues for individuals with color blindness. The color pattern and location all need to be standardized and implemented in every vehicle in order to ensure that consumers can immediately identify the level of autonomy upon entering any manufacturer's vehicle. And this also needs to go along with an airline industry type training. Since most people will not study the SAE levels of autonomy on their own, they need to be taught those levels and their significance. Each
2 minutes left.
Okay, thank you. Each state should implement a driver training program, which students have to pass in order to receive a license to operate an autonomous vehicle. The training needs to include a physical ride in a level 3, level 4, and level 5 vehicle as they become commercially available, since not all of those levels are available now. It also needs to include information on autonomy levels in the color system and basic safety and error response training. And we expect that understanding autonomy levels and capabilities should increase or decrease, crashes and improve public opinion. I also have a list of my references here. And then finally, I would like to thank my report co-authors, Stephen Semrau, Chance Gattle, and Charles Gates, our faculty advisors who helped with this project, as well as our SWE counselor, and the sponsors of the Auto Drive Challenge. And with that, I would like to turn it over for any questions.
Hi, so I like what you did here. Seems like there's a lot of results that you talked about that seem very different. So what would you say was the primary goal and result from this project?
I would say the primary goal of the project was to figure out the big players in autonomous vehicle safety. And I think that probably our largest and most significant results hinged around the pedestrian diversity issues, And then also on the need for training, that's something that our team has taken further steps on to write additional reports and papers on, because there's a really big lack in any information on that right now.
Okay.
So can you help provide some knowledge to this team of what the differences between level 3, 4, and 5 are for autonomous vehicles?
Yeah, absolutely. So I actually have a backup slide on that right here. So this is the SAE levels of driving automation, and levels 0, 1, and 2 are the typical ones that we see right now, things like cruise control or maybe adaptive cruise control, lane keep assist, and things like that. And then as we start getting into level 3, 4, and 5, that's more of what we start to think of as actual autonomy. So a level 5 is the most autonomous, meaning that the vehicle can drive itself no matter what, everywhere that it goes. And in level 4, the vehicle can drive itself, but only in certain scenarios. So maybe it can't do rural driving, but it's very good at city driving, and then the human would never have to take over during city driving. And then level 3 is one of the more dangerous levels, and essentially the vehicle is capable of driving itself in very limited conditions. And when those conditions suddenly change, the driver of the vehicle will need to take over very, very quickly with very little warning.
So you mentioned you created your own data set for accessible the population of the group. How much is the ratio compared to the other data set that is existing? Like, what does your sample set look like?
The current existing data sets are significantly larger than what we've taken on our own. We have, as of right now, because this is something that is relatively recent for us, starting to build this new data set, we have, I would say, maybe 10 to 15 images that really focus on diversity right now. And most of our other images were just taken driving around in our area, which is Flint, Michigan, and just seeing whatever we see at that time.
And have you looked into data augmentation at all to just increase your sample set?
Not quite yet.
Okay. We have about a minute left. Any final questions? Okay, then. Thank you so much, Olivia, for sharing your work with us.
Thank you.